Gold geologically doesn't just form one way, but again, this is an introductory class. We're just going to talk about a very common way that gold forms. And what I've drawn here is the surface of the land. Right? There's a tree there. A magma chamber here. Nothing's to scale. It's all cartoon format. But remember that as this thing begins to crystallize, as our magma chamber is crystallizing, there's a bunch of stuff contained in that magma that doesn't want to be a solid crystalline igneous rock. And so what happens is there tends to be this residual fluid. I would call it water, but that's not a very good, it's not a good way to think about it. It's a fluid filled with metals and minerals and all kinds of weird stuff. And so as this thing begins to cool, first of all, it will start to fracture because it's shrinking, right? These things kind of shrink as they cool, just like most things would. So this fluid gets forced out, and it can also get forced out into fractures in the surrounding rock. Those things tend to get mineralized. I'm sure you recognize this diagram from our discussion on hydrothermal vein deposits, right? That's kind of where we're headed here. So we get this mineralization zone surrounding these fractures. It's warmer down here. I wrote warm, I should have written hot. Let's just think. It's hot down there. It's cold up here. And so there's a temperature gradient as the hydrothermal fluid is working its way off through the surface of the land. It will actually deposit minerals according to temperature, because those minerals are sitting in that fluid. That fluid's going towards the surface and it's cooling off. And minerals are getting left behind in their kind of preferential temperature zones. So kind of backing off of this kind of crummy cartoon diagram, you can see here something a little bit more serious, which is showing a hydrothermal system, right? So it's not just gold. And maybe you can see over on the far right-hand side of this image, there's a bunch of minerals listed. And if you look for the chemical symbol AU, right? Remember that's our gold buddy. You'll see that there. You'll also see AG, which is silver. You'll probably see, lead and iron, a couple of other things in there as well. But those very specific kind of combinations of gold drop out at specific temperatures. You can see here, these are some pretty cool vein type deposits. So again, under the right conditions, as these fractures exist and water is flowing through them, they're leaving behind this mineralization. So whether it's kind of fractures that have occurred this way, whether it's a fault, so oftentimes these things will follow faults. There can be all sorts of kind of geological control on where we have the fractures, but the fact remains that this gold is existing and being deposited by those hydrothermal fluids. So I've drawn this diagram to kind of highlight how we recover gold. And really, there's kind of two end members, and these are things that you've seen before so far in this course. One of the things that we could talk about is hard rock mining. So I've drawn here a hill, then I kind of did this crosshatched pattern. Let's say there's gold mineralization or a series of gold veins that runs along there. So we could go down and excavate that gold vein. That would be one type of mining. But another thing that happens is as that is kind of eroded, gold, which remember, it's chemically stable and it's really heavy, it tends to kind of stay back, will ultimately wash out into sands and gravels and depositional environments and be part of the sediment itself for quite a few reasons. So again, it's heavy, it's chemically durable, right? It doesn't dissolve, and so it'll tend to concentrate in what we would call placer deposits, right? So this would be hard rock, this would be placer. And then I've actually included a third type, which is hybrid, meaning hybrid, it's a little bit of both. So you could also have had the situation where this then gets buried or kind of there's more sedimentation that takes place, and ultimately these become lithified into like a conglomerate or a sandstone or something. So it is a hard rock, but it contains gold that was like a placer deposit. And actually the reason I bring that up is historically, the most productive gold deposits on Earth in South America or in South Africa are kind of this hybrid type deposit. So just thinking about how this works, here's a kind of cartoon cross section of an area in South Africa as the gold is being deposited. So you can see kind of the hills, the volcanoes. So there's, you know, hard rock sources of gold, but hopefully you can see in this diagram, the streams are kind of flushing that gold out into deltas, into these lake sediments. And if you look closely at the stratigraphy or the strata, you can see there's these layers of what we call conglomerate, which is a sedimentary rock that's like sand and gravel, right? Larger pieces. So those will tend to concentrate gold. So now if we kind of blast forward and we look at, here's a map of a gold production region in South Africa, or one of the most famous gold production regions in South Africa. We have this kind of central highland, and it was shedding gold off, and you can see shown here in blue, and almost this kind of like arcuate form, or curvilinear, that's one of my favorite words. Those are places where the gold kind of shedded out and settled, and then later this was all lithified, right, as a competent sedimentary rock, and so now we're excavating that. So thinking back to our giant cube of gold, right, remember there was 65 feet on each side, just shy of 25% of that, if you were to slice off 25% of it and take that gold, that's the gold that's come out of South Africa. It's incredibly productive gold mines down there. That's no longer the case. They were surpassed in the 70s by China, but really, again, from kind of modern history, South Africa has led the way, but they're no longer top dog. Again, once we've recovered our gold, generally hard rock or you know, lithified sedimentary rocks, we take that ore, right, those rocks that contain low amounts of gold. You know, the idea that you can just go and excavate a gold vein is not realistic. It's generally kind of micro distributed throughout rocks. So it's not so easy to go get, kind of think about gold flecks being distributed through igneous rocks. We take those rocks, we excavate them, right? We remove them, and we crush it into basically a really fine sand. You guys have seen this picture before, but this is some gold ore from here in Idaho, and it doesn't look like much, right? It just looks like a handful of dirt. Geologists hate the term dirt. It's soil. But this isn't soil. This is really fine-grained, kind of on the border between a silt and a sand when you think about grain size. But now we have this stuff that has a very low percentage of gold in it, and we have to take advantage of some of the interesting properties of gold to recover it. So a very common way to do this is to dissolve the gold. I mentioned earlier that gold is notoriously resistant to acids, although there are some acids that will dissolve gold. And particularly, we use cyanide, alkaline cyanide, and that cyanide will dissolve preferentially gold. And so with that notion in mind, what we do with this stuff, this is what we call cyanide heap leaching, and it's a really common method of gold extraction. It's been used all over Idaho, it's been used all over the world, where we basically take this material, this ore, this powdery, fine-grained sand, and just make a big heap of it. Underneath that, we line it with some sort of liner, like a giant rubber pond liner, if you were to kind of simplify it. And then what we do is again, simplifying, we basically just take a sprinkler system and just apply cyanide to that heap, and that cyanide just flows through. Again, we're making coffee, basically, right? Cyanide is flowing through that heap, that pile, and when that cyanide goes through, it's melting out all those little tiny bits and pieces of gold, and then at the end, it's collected in these ponds, and those ponds are now filled with cyanide that has lots of dissolved gold in them. We can use kind of some electrostatic precipitation, we can do some other processing to that cyanide and chemically pull the material out of those ponds. that process, like I said, is probably not worth our time to go through how we pull it out of the cyanide. Back in the olden days, we used to do this with mercury, because mercury does the same thing, but we all know how toxic mercury is. And it will dissolve gold in a very similar way. And then you can actually just cook it and blow off the mercury into the atmosphere, which you should all be like shrieking in your seats or however you watch these videos. We blow the gold off, just boil it off, or boil off the mercury, and what's left behind is gold. We definitely don't do that anymore. But another method that I wanted to talk about is something, and we don't just do this for gold, but it works for gold. We can find very particular bacteria, in specific a group of bacteria-like organisms known as archaea. They don't survive with photosynthesis. They largely survive by the process of chemosynthesis, meaning they consume chemicals for their energy. Minerals, they're eating chemicals. Things that live on the hydrothermal vents in the seafloor use chemosynthesis. And so we can get some chemosynthetic archaea or chemosynthetic bacteria and actually inoculate this ore, just like we were talking about, and it will go into minerals that are bonded with sulfur in particular, and it will strip the sulfur off and consume it, leaving us with the concentrated metal behind. So that's called biomining, biological mining, or bioleaching. We do it with a couple of different metals. It is used. It's not as widely used because it's really expensive, and you actually have all this pretty nasty bacteria to deal with. So it's not as bio as it sounds. It's not really like green mining, if you were to think about it in that sense.